Hi, I'm Preston Bone.
I'm Quan Brown.
I'm Dustin Browning.
And I'm Robert Bowler, and this is our project for the optimization of a disk launcher for Mechanical Engineering Design Studio. Here's a brief overview of what we're going to be talking about tonight in our presentation. First, the introduction, then our design process, then the design description, testing methods, budget summary, and conclusion.
We have our problem definition, which is just a few constraints we had to consider. It was the cost, couldn't spend more than $40. We had size, which was 2.5 feet by 2.5 feet by 2 feet. Had to be smaller than that. We had the weight, which had to be able to carry by one person. It had to be safe, and we just had to store that energy inside it. It couldn't be energy from outside the device. It had to be foot activated.
So we're building this launcher to compete in the competition. The competition works where two teams compete against each other, and the team with the most points moves on to the next round. In order to calculate how many points we get, we first need our throw points. Our throw points are calculated by figuring out where our disk lands inside of the target multiplier and then multiplying that number by our throw distance. In order to find our overall points, we need to take our throw points minus 5 times the machine cost.
So to first come up with some concepts, we looked at a lot of different outside sources. We first looked at siege weapons because, as we all know, civil engineering is the oldest form of engineering, but military engineering is the second oldest form. People have been trying to figure out how to throw projectiles for thousands of years. We also looked at two very specific designs. We looked at a shotgun clay thrower, and we also looked at a frisbee thrower. And then we used these to come up with some potential designs.
Here are the 6 designs we came up with. These are sketches straight from our design notebook. The first 3 designs, including our datum, involve an arm and a spring which launch the device. Design 3 is modeled after a crossbow. Design 4 after a catapult. And design 5 is a spinning disc with a track set on it. To determine which of these devices we're going to use, we use the decision matrix with the constraints of safety, consistency, distance, estimated price, setup time, durability, roll amount, size, and weight. At the end of this, we came up with a discussion between device 2 and the datum, but ultimately, due to the practicality of device 2, we went with the datum.
We have our final design description, which is very simple. We had a couple of triangles that we built, and then we had 5 supports running between them. As you can see here, here's the triangles, here's the supports. We then built an arm out of a couple of 2x4s, notched a 2x4, attached one on the bottom and on the side, and that gave us this arm with the notch in it, and then we just simply attached it with a bolt and nut.
Once we had our design built, we had to test it to see what it was capable of. In order to test the design, we took it down to the IM fields and we loaded it and we launched the disk 12 times. Each time when we launched the disk, we walked out and we measured the X component and the Y component, and we took an average of them to get a good feel for what the launcher was capable of.
So here we calculated the max throw distance from the center of our launcher. And so the max throw distance had an average of about 49 feet from the launcher, and this was shooting at an angle of about 61 degrees from the vertical of the machine. And so we had a max throw distance of about 55, and we had a mid of about 46. This gives us a range of about 9.16 with a standard deviation of about 2.5. So not a terrible amount of spread, but definitely not as concise as we would want it to be. As we can see here, the spread represented in the graph, almost all of them would be in the ×6 multiplier, except the one outlier here. And we have the maximum distance from a launcher. We thought that would degrade as the spring was used more, but we only have 12 data points, so we can't really draw any conclusions from this data. And our angle was at a consistent 61 degrees from the vertical.
So we also have our budget, which is just a couple of things we had to take into consideration. We had the first round, I suppose, if you wanted to think of it that way, of costs that we had, just the wood, spring, the washers, that sort of thing. That totaled out to $19.45. And then we had that second round, that improvement stage that we went through, and it just increased the cost to $20.54. That just simply included a spring and some washers. So,
After the final device was built and tested, we had a very good grasp for what to expect from this device, and there were a lot of good things that came out, but a couple of bad things that came out as a result. So we realized that our launcher pretty much lands our discs at an angle 60 degrees to the left of where we're launching it from. That is a manageable problem. We're just going to move our design so we don't have to launch it straight. We also have our disc launching at a 45-degree angle, and we realized that if the disc was at an angle, when it reaches maximum height, it would start to fly backwards due to like wind resistance. And as a group, we learned about what it takes to design a gadget as an engineer, and we realized the importance of communication, trust, safety, precision, and teamwork.